Recording in progress. So welcome to video number 2 in our chapter 10. So now go to the torque and angular acceleration of your rigid body. Okay. So here we applied actually a force. So force has component Fz, F1z. It also has a radial component and also a tangential component. So this is the axis of rotation along the z-axis. So we have y and x. So this is the path of a particle as body rotates. So, okay, this particle of mass m1. So we can see here that only the tangential force produces what we call this one, a component of torque. So the radial and F1z does not uh, produce a component of torque. Okay, so if that's the case, so therefore the Newton's second law, so F1, this tangential is just equal to the mass m1 times the acceleration, tangential acceleration. Okay, so from our previous discussion, so this a tangential, a1 acceleration, tangential acceleration is just equal to the r1, okay, times the angular acceleration along z. Okay, the tangential acceleration is just the rate r this r1 times this one. Okay, if we multiply both sides, this equation multiply both sides by r1, so we have f tangential, okay, times r1, okay, and we have here uh, in the other side is m1 r1 uh, alpha z, okay, r1, okay, what will happen is that in the left hand side will become m r1 squared alpha c, okay, or m1. So in the left hand side, is just the torque, okay, the torque along the z-axis, the torque of this uh, mass m, and we know that the moment of inertia is equal to m1 r1 squared, okay, so we have here I1 alpha 1 z. Actually, this is alpha 1, alpha 1 z. Okay. So we write the equation like this for every particle in the body and then add all these equations. So if we have uh, for example, we have for every particle, so meaning we have the torque 1 plus the torque 2, okay, z is just equal as a plus that. So this is equal to m1 r1 squared alpha z 1 plus m2 r2, so angular acceleration 2 along z plus that. So here, so we have that the summation of all the torque, okay, torque I z is equal to the summation of is equal to the summation of mi ri squared, which is we know that this is just the definition of the moment of inertia alpha z, okay, alpha 1, alpha 2, or alpha z, okay. So by the way, we can this is just this one you can just put as equal to uh, angular acceleration along z, okay, the same acceleration. So they have the same acceleration, so we can factor this one out. So meaning we have now what we call the rotational uh the 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 net torque along z is just equal to the I times the angular acceleration, the moment of inertia. Okay. We call this one as the rotational analog of the Newton's second law for a rigid body. The net torque on a body about the z-axis is equal to the moment of inertia of the rigid body about the z-axis times the angular acceleration of the rigid body about the z-axis. So if you loosen or tightening a screw, requires giving an angular acceleration. Hence, it requires applying a torque. Okay. This is the rotational analog of the Newton's second law for a rigid body. Here, this explains why the only the external torques affect the rigid bodies affect a rigid bodies. So because if you have any two particles in the object exert equal and opposite force on each other. So we have here the F1. So an action force pair whose torques cancel. Okay, because this is the lever arm. So if these two particles have uh, equal in magnitude, opposite in direction, so this would be the if you add in one, it will become zero. Okay, that's the reason why only external torques affect the rigid bodies of rotation, not the internal torques. Okay. So here we have a problem solving strategy: identify, set up, execute, and answer. Okay. So we have here an example, unwinding cable 1. So this is in the figure 10.9a, shows a situation analyzed in example 9.7. We use this energy methods. Okay, this particular example, what is the cable's acceleration? Okay, so if we draw the free body diagram, so we have here the normal force. So the weight of the normal force both act on the line to the axis of rotation, so they exert no torque. We have this direction, the weight, and we have here the force, which is the 9 Newton. And we have given the radius, which is equal to 0.6 meters. Okay. So using the definition that the torque, okay, Z is just equal to, or the net torque is just equal to the moment of inertia, this body times the angular acceleration along Z. So what is the cable's acceleration? If you want to find the acceleration of the cable, so we have here that the torque uh, over I. So here, the torque here is just equal to R times. So the torque in this particular is just equal to FL. So in this case, F is 9 Newton, 9.0 Newton, times L is just equal to R, which is equal to 0.06 T meters. So this is equal to F times R. Okay, here, the torque is FR, and the moment of inertia is equal to M, for in this particular, M cylinder squared over 2. Okay, so we have 2FR over M uh, R squared. So meaning you can cancel this one. So we have 2F over MR. Okay. So here we have 2 times 9.0 Newton, okay, over the 50 kilograms. So 50 kilograms weight, okay, multiplied by R, which is 0.06 meter. Then you can calculate the angular acceleration. So 2 times 9 over 50 times 0.06. So we have our answer is 6 0 radials radians per second squared. So that is the answer. Okay, so take note of the what we call this one. What is the cable's acceleration? If you are interested in finding the tangential acceleration, A tangential is just equal to R times the this one. So we multiply 6 by so equals times 0.06. So we have 0.06 meter times 6.0 radians per second squared. So you will have here 0.36 meters per second squared. Okay. 0.36 meters per second squared. Okay, that's how you use the definition of the rotational dynamics. Okay, again, we have here another example. So we have here what is the acceleration of the falling block and the tension in the cable? So review example 9.8. Okay. So here, if you look at the Fibry diagram, so we have the normal force in this direction, okay, and we have here the weight force, and we have here the tension, which is the only one that's producing the torque. And here we have again we have the tension T, and we have here that the mg. So we treat this one as our positive y. Okay. So from the Newton's second law, so this is one is accelerating. So we have here ay is along that in that direction. So from the Newton's second law of the block, uh, of the block, so we have here that mg plus the negative tension is equal to m-a-y. So this is the mass of the block. Also from the definition of the net torque, okay, so the torque here is just equal to uh, the RT, okay, are the force times this one, so the tension times the radius. So this is actually equal to the moment of inertia of this one and the angular acceleration. So the moment of inertia is 1/2 m r squared alpha z. Okay, so that is the okay. As example 10.12, the acceleration of the cable is the same as the tangential acceleration of the point on the cylinder ring. From equation 9.14, the acceleration ay, okay, we know that the acceleration ay here is just equal to the a tangential, which is equal to r alpha z. Okay, we use this to replace this one here. Okay, up in the cylinder equation above and divide by r to get the result t. Okay, so let's divide both sides. So since we have RT is equal to 1/2 M, okay, R times R alpha Z, okay. So this is actually, this is AY, so we have here, so we divide both sides by R, okay, R, okay, will cancel out. So our tension is equal to 1/2 times M, so this is a big letter M, M times AY, okay. So from here, so from this one, so we have our what we call this one from this equation one, okay? So we have mg minus 1/2 times m, or the mass of this cylinder, ay is just equal to m ay. Okay, so here m AY plus 1 half MAY is equal to MG. Okay. So this is a big letter M. Okay. So AY is actually MG over M plus uh, so by the way, M plus M over 2. So M over 2. So or we can write this one as G over M 1 plus M over 2M. So that is the this equation. So so that is the acceleration of the falling block and the tension of the cable. Okay. To get the tension, okay, for the tension T, okay, here T is just equal to actually mg minus MAY. So here uh, we have mg minus m times g over 1 plus m over 2m, okay, which is equal to mg over 1 plus 2m times m. 2m over, okay, over m. Okay, so you need to simplify, know how to simplify this one. So that is the tension and the acceleration of the block. Okay, so uh, done for this video. So please click the subscribe and the like button for more videos like this. See you in the third video.